Good morning, students. Welcome to Bindu Dhadwal chemistry lessons. Today we'll be doing a few properties of phenols. So the chemical properties of phenols can be classified into three types: reactions of phenolic group, that is OH group, reactions of benzene ring, and special reactions. Today we will try to cover reactions of phenolic group. So first is acidic character. Phenols are weakly acidic in nature. So they will be showing properties of acids. They turn blue litmus red. They react with alkali metals to release hydrogen and with alkalis to form salt and water. But phenol is a weaker acid than carboxylic acids. Carboxylic acids also show other properties of acids, like they will react with sodium carbonates and bicarbonates to produce carbon dioxide, but phenols do not react. The of phenols is because of the presence of polar OH group. Now, in phenols, this OH group is attached to sp2 hybridized carbon of phenol. This carbon, in comparison to alcohols, has higher electronegativity. So this makes this bond more polar. Electron density on oxygen atom decreases because of polarity of this bond, and it will take these electrons, facilitating the release of proton. So it's acidic in nature. To explain the acidic nature of phenol, we see that phenol and phenoxide ions are both resonance stabilized. Their acidic character can be explained on the basis of resonance. Phenol is a resonance hybrid of following structure: C6H5 and OH, and another structure will be where the bonds are on alternate position. Then we can draw some more resonating structures of phenol. Drawing. These electrons move to this side and electrons will come over here. So in structure 3, we see that there is a positive charge on oxygen atom, negative charge on this atom, and 2 bonds over here. In the next structure, these electrons move to this side, these electrons move to this carbon atom. So we get structure number 4. Again, there is a positive charge on phenolic oxygen, and a bond comes over here, negative charge here, and bond is placed here. In the next structure, these electrons move to this bond, these electrons move to this atom. So we get structure number 5, where we again have a positive charge on oxygen atom, and we have double bond here, double bond here, and negative charge here. So out of the 5 resonating structures of phenol, we see that structure 3, 4, 5, they have positive charge on phenolic oxygen and negative charge in the ring. So these 3 structures will attract the electron pair of OH bond strongly towards itself because of the positive charge and facilitate the release of proton. So phenol, because of resonance, will tend to release the proton. Phenoxide ion is also resonance stabilized. One structure when proton is lost is phenyl ring with oxygen atom with 6 electrons. Second structure will be where the double bonds are on alternate position. In the third structure, these electrons will move here and these electrons to this atom, but after formation of the structure, we see that there is no charge differentiation. Negative charge is there, and in the next structure, electron move here and these electron move to this carbon atom, resulting in structure number 9. So let's draw this structure. Double bond, 4 electrons, double bond here, negative charge here, and a double bond here. Now in the next structure, these electrons move here and these to this carbon atom. So we get the structure number 10. So in the structure number 10, the negative charge has come here. There's a double bond with oxygen, 4 electrons, double bond here, and a double bond here. So both phenol and phenoxide ions are stabilized by resonance, but phenoxide ion is more stabilized because there is no charge differentiation here, whereas in structures of phenols there was positive as well as negative charge. Also, electronegative oxygen by nature is having positive charge, which is contrary to its nature and will not contribute more to resonance. So phenoxide ion is stabilized more by resonance. So in this reaction, this is more stable than this. So reaction will tend to move in the forward direction, facilitating the release of proton ion. Thus phenol is acidic in nature. Reaction favors forward direction. In comparison, alcohols, neither the alcohol nor alkoxide ion is stabilized by resonance. So phenols are more acidic in nature than alcohols. We can compare the values of different structures by their Ka and pKa values. Larger the Ka value, more acidic is the compound. Effect of substituents on the acidic character of phenols. So any group that stabilizes the phenoxide ion more will increase the acidity. So electron withdrawing groups will take the electrons away from the oxygen, thereby decreasing the electron density so that it can take electrons from the oxygen-hydrogen bond and facilitate the release of proton. So electron withdrawing group increase the acidic strength of phenols. So like nitro, cyano or halo group will increase the acidic strength. On the other hand, electron donating groups like amino, alkyl or alkoxy give electrons and intensify the charge on the phenol and thereby on the oxygen atom. So the tendency to take electron decreases, so acidic strength also decreases. Example, phenols pKa value is 9.98, but an electron withdrawing group, chloro, when attached to it, decreases its pKa value, so it is more acidic in nature. Similarly, para-nitrophenol is most acidic in nature. More the number of electron withdrawing groups, more will be the acidity. For example, and electron releasing groups will decrease the acidity. So we see that para-aminophenol is less acidic than phenol, and para-methoxyphenol, the value is again greater, pKa value is greater than phenol, means it's less acidic than phenol. Similarly, paramethylphenol. The particular effect is more significant when the substituent is present in ortho or para position than meta position to the OH group. Electron withdrawing group like nitro group is present at para position of OH group. Then the effect of electron withdrawing group is maximum. So acidic character is increased. Orthonitrophenol than metanitrophenol, and phenol is least acidic. Nitro group has both minus R effect and minus I effect. In case of ortho and para compounds, the minus R effect will predominate over the minus I effect. Nitro group, when present at ortho and para position, it withdraws electron by stronger minus R effect. Conjugation is extended to the oxygen atom of the nitro group. In case of metanitrophenol, there is no resonance effect, only minus I effect, and because of minus I effect, the acidic character is increased. Orthonitrophenol is slightly weaker
the acid than para-nitrophenol, because in ortho-nitrophenol there is weak hydrogen bonding, intramolecular hydrogen bonding. Intra means within the molecule. When this is attached with hydrogen bonding, the release of proton will be difficult as compared to para-nitrophenol. The comparison of acidic strength of crisols or methyl phenols. Now, methyl group, being electron releasing in nature, will intensify the negative charge on this oxygen atom, thereby decreasing the tendency of oxygen to withdraw electron of the OH bond towards itself. So, acidic character is weakened. Methyl group will have plus I effect as well as hyperconjugation effect. Both these effects tend to intensify the negative charge on the ring and the oxygen of the OH bond, thereby decreasing the acidic character. But the hyperconjugation effect predominates over plus I effect. Both these effects will increase the electron density in the OH bond so that the loss of proton becomes more difficult. What we see is that phenols will be more acidic than metacrysols, will be more acidic than paracrysol, will be more acidic than orthocrysol. In metacrysol, there is no hyperconjugation effect. It is showing plus I electron releasing effect. This electron releasing effect decreases with increase in distance from the reaction center. So the plus I effect will be less in para position than in ortho. Acidic strength of aminophenols and methoxyphenol. An amino group and a methoxy group, when attached to benzene ring, has plus R effect. It will intensify the negative charge on the oxygen atom. This is due to presence of lone pair of electrons on nitrogen or oxygen atom. These groups will also show minus I effect. This is because of electron withdrawing nature of nitrogen and oxygen. Both nitrogen and oxygen are more electronegative than carbon. So what we see that because of plus R effect, the negative charge is intensified. So ortho and para amino phenols will be weaker acids than phenols. So when amino group is present at ortho and para position with respect to OH group, it increases electron density on the OH bond by plus R effect of amino or methyl group, thereby electron donating group means less acidic character. However, when amino group is present at the meta position, we see that resonance will not affect the carbon bearing the OH group. The electrons move here, here, and then they move on to the next bond. They do not come to this bond at all. So, plus R effect will have no effect in case of meta amino phenols. However, amino group is electron withdrawing in nature. It is more electronegative. It will withdraw the electrons. So due to minus I effect, it withdraws the electron from all the nuclear positions of benzene ring and will withdraw electrons of the OH bond and will increase the acidic character. So meta-amino-phenol will be more acidic than phenol. Similarly, meta-methoxyphenol is more acidic than ortho and para-methoxyphenol. Now, minus I effect of methoxy group is more than that of amino group. So, meta-methoxyphenol will be more acidic than meta-aminophenol, which is more acidic than phenol. On comparing ortho and para-methoxyphenols, plus R effect in ortho position is less than at para position because of steric hindrance. So as a result, the increase in electron density in OH bond is less in case of ortho-methoxyphenol. So in this case, Metamethoxyphenol will be more acidic than orthomethoxyphenol, will be more acidic than paramethoxyphenol. Comparison of acidic strength of halophenols. Now halogen have both plus R effect and minus I effect, but minus I effect predominates over plus R effect. So all halophenols will be more acidic than phenol except parafluorophenols. As we know that minus I effect decreases with distance, so acidic strength of halophenol will be ortho-halophenol will be more acidic than meta because minus I effect will be maximum. Electron withdrawing effect will be maximum. So this will be stronger acid than meta-halophenol than para-halophenol. Ortho-halophenols, the acidic strength of halophenol decreases as minus I effect of halogen decreases, except orthofluorophenol. So chlorophenol is most electron withdrawing in nature, so it will be most acidic than orthobromophenol, then orthoiodophenol, and orthofluorophenol will be the weakest acid because hydrogen bonding is maximum with fluorine. So this hydrogen bonding will result in it being the weakest acid. Other reactions of phenolic group of phenol are action with zinc dust. When phenol is heated with zinc dust, it is reduced to benzene. Action with ammonia, when phenol is reacted with ammonia in presence of anhydrous zinc chloride at a temperature 675 Kelvin, amino group will substitute OH group. So aniline will be formed along with water. Action with acid chlorides and acid anhydrides. This when phenol reacts with acid halide in presence of pyridine or acid anhydride in presence of a little bit of concentrated sulfuric acid, the H of phenolic group will react with Cl to form HCl, and COCH3 group will be attached and ester will be formed. This is phenyl ethanoate. And similarly, in case of reaction with acid anhydride, the H reacts with acetate group of acetic anhydride and acetyl group is introduced. So ester is again formed. As acylation, acyl group is introduced in phenol, this reaction is known as acetylation reaction. This reaction is important when we carry out acetylation of salicylic acid, that is OH at ortho position to benzoic acid. When we react it with acetic anhydride, then this OH group will be reacting with the acetic anhydride to introduce acetyl group here. So we get acetyl salicylic acid. This is called aspirin. It has analgesic properties, that is, it reduces pain, anti-inflammatory properties, it can reduce inflammation, and antipyretic properties, it can reduce fever also. So it's important medicine, aspirin. When phenyl acetate is heated with anhydrous aluminum chloride, it undergoes rearrangement. Anhydrous aluminum chloride, this COCH, this H will come to this position, COCH3 comes here. So there is a rearrangement at ortho and para position. Ortho hydroxy acetophenone is formed and para hydroxy acetophenone is formed. This reaction is known as Fry's rearrangement. When we react phenol with benzoyl chloride in presence of sodium hydroxide, H combines with Cl to form HCl, benzoyl group is introduced, phenyl benzoate is formed. This reaction is called Schotten-Bowman reaction. And like with alcohols, phenols also react with Grignard reagent, give H to the alkyl group of Grignard reagent to form respective alkane, and phenoxymagnesium ionide will be formed. So that is all in today's topic. Thank you. Have a nice day.